much of our time. Yesterday we have studied about the very important reactions. First we have studied about the addition of the halogens. So when halogens are added in the presence of CCl4, they gives us the vicinal dihalide, as you can see here, 1,2-dibromoethane vicinal dihalide. We have seen the various reaction of the halogen exchange, which are also known as the Finkelstein reaction and Schwarz reaction. Finkelstein reaction is the reaction for the preparation of alkyl iodide, where this alkyl chloride or alkyl bromide are allowed to react with the sodium iodide in the dry acetone, so that we can get alkyl iodide and sodium chloride or sodium bromide. The sodium chloride and sodium bromide are insoluble in acetone, so they get precipitated, and as they get precipitated, they can be removed from the reaction mixture, and according to Le Chatelier's principle, we get more and more product. Same way we have the Schwarz reaction. Schwarz reaction is used for the synthesis of the alkyl fluorides. So when we have alkyl bromide or alkyl chloride, we allow it to react with the fluorinating agents or metallic fluorides such as silver fluoride, mercurous fluoride, cobalt fluoride, or antimony fluoride, so that we can get alkyl fluoride and silver bromide or silver chloride. This reaction is termed as Schwarz reaction. The reactions of fluoride is very vigorous, and that is why Schwarz reaction is preferred for the preparation of alkyl fluoride, which is comparatively safe reaction. Now we'll understand about the preparation of the haloarenes. We'll first study the preparation of haloarenes from the hydrocarbon by the electrophilic substitution. Aryl chlorides and bromides can be easily prepared by the electrophilic substitution of arenes with chlorine and bromine respectively in the presence of Lewis acid catalysts like iron or iron 3 chloride. You can see here, my dear students, that in this reaction we have a toluene. This toluene, when reacts with the halogen X2 in the presence of iron, light should not be present, so dark is needed. Thus, orthohalotoluene and parahalotoluene are being formed. This orthohalotoluene and parahalotoluene, they have a large difference in their melting point, and then by using the process of melting, we can separate them. So this is how, my dear students, we understand about this preparation. Reaction with iodine is reversible in nature, and that is why some oxidizing agents are needed if we want to prepare the aryl iodide. This aryl iodide can be prepared by the presence of the nitric acid HNO3 or periodic acid HiO4. This nitric acid and periodic acid oxidizes this product HI, which is a byproduct, to iodine, and this is how according to the Le Chatelier's principle, the byproduct is removed from the reaction mixture, and we can get more and more or maximum product by this way. So this is how, my dear students, we can understand about the preparation of the various compounds. Fluorocompounds are not produced by these methods because they are highly reactive and the processes are vigorous. We can understand the same with the other examples, even, my dear students, that let us try to look at them. If we take benzene and allow it to react with Br2 in the presence of FeBr3, which is a Lewis acid, we'll get the bromobenzene and HBr. If we take benzene and allow it to react with chlorine Cl2 in the presence of FeCl3, we'll get chlorobenzene and HCl. Now we need to understand preparing diazonium salt. So please remember, my dear students, that on benzene, if you have N2 plus and Cl minus or N2 plus and X minus, such compound is known as the benzene diazonium halide. Here this bond N2 is known as diazo bond, and that is why it is known as benzene diazonium halide. When a primary aromatic amine dissolved or suspended in a cold aqueous mineral acid and then treated with the sodium nitrite NaNO2, a diazonium salt is produced. You can see here that the diazonium salt is produced. Yesterday we have discussed even the whole process. You can see here mixing the solution of freshly prepared diazonium salt with cuprous chloride or cuprous bromide will give us the chlorobenzene or chlorobenzene. You can see that diazonium chloride when reacts with CuCl2, it produces chlorobenzene. Diazonium chloride when reacts with CuBr2, it produces bromobenzene. So this particular reaction is known as the Sand-Meyer's reaction. So we call this reaction as a Sand-Meyer reaction. Please remember this reaction is known as the Sand-Meyer reaction. Replacement of the diazonium group by iodine does not require the presence of cuprous halide. Means you don't need cuprous iodide, but the reaction can be done in the presence of potassium iodide and done simply by shaking the diazonium salt with potassium iodide. You can see that diazonium halide in the presence of potassium iodide will give us the iodobenzene. So this is how we can prepare the chlorobenzene, bromobenzene and iodobenzene by the use of the diazonium salt or Sand-Meyer reaction. Why is sulfuric acid not used during the reaction of alcohol with potassium iodide? My dear students, we know that sulfuric acid is a very strong acid. This sulfuric acid converts these iodide ions into iodine. If it is potassium iodide, then first it converts to hydrogen iodide and then hydrogen iodide to iodine. Or if they are hydrogen iodide, they can be directly converted to iodine. Thus, when we are converting alcohol into the alkyl iodide, these iodide ions are needed to replace alcohol so that we can get alkyl iodide. But all the iodide ions are converted to iodine, or all the iodide ions present into the potassium iodide or hydrogen iodide are converted to iodine by the strong oxidizing agent sulfuric acid, and that is why uh, uh, and that is why this and that is why we should not use sulfuric acid while we want to convert the alcohol into the alkyl iodide. So this is how we can understand, my dear students, that the reason, which is an in-text question given into your textbook. Let us look at the next in-text question, my dear students. Write the different dihalogen derivatives of propane. You can see here, my dear students, that propane gives four dihalogen derivative. One is 1-chloropropane, 1,1-dichloropropane, another is 2,2-dichloropropane, uh, next one is 1,2-dichloropropane and 1,3-dichloropropane. 1,1 is and 2,2 are called geminal, 1,2 are called vicinal, whereas 1,3 is called terminal dihalides. Among the isomeric alkanes of formula C5H12, identify the one that on photochemical chlorination yield a single monohalide. My dear students, we know that neopentane, which is when allowed to react with the chlorine, will give us the monohalide, whereas my dear students, the isomeric monochlorine, normal pentane, when it is allowed to react with chlorine, it will give us the 1-chloropentane, 2-chloropentane and 3-chloropentane. So three various isomers. At the same time, my dear students, the 4-isomeric monochloride is given by the isopentane. You can see that chlorine when reacts with chlorine when combined here, the 1, then here 2, here 3 and here 4. So these are the four various compound that can be prepared. I am going to tell their names. I have written the names as well as the numbering even has been shown to you so that you can easily understand it. The various isomeric monochlorides formed are the 1-chloro-3-methylbutane, 2-chloro-3-methylbutane, 2-chloro-2-methylbutane, and 1-chloro-2-methylbutane, my dear students. Now we shall study about the next question, which is the in-text question. Draw the structures of the major monohalo product. So this is what we have studied, that cyclohexanol give a chlorocyclohexane. The um, nitrophenylethane will give us the 1 bromo 1 nitrophenylethane. The benzyl alcohol or hydroxybenzyl alcohol or hydroxyphenyl benzyl, we can say para hydroxybenzyl alcohol, will give us the para hydroxybenzyl chloride. The cyclohexene or methyl cyclohexene will give us the iodomethyl cyclohexene, which is the Markovnikov product. The CH3CH2Br with the Finkelstein reaction will give us the CH3CH2I, and in the presence of ultraviolet light, there will be free radical mechanism will give us the uh, um, 5 bromo cyclohexene. So here this, if we give the numbering, we can give the numbering as 1. This is the 1, 2 and 3. So this is how it is going to be 3 bromo cyclohexene. Please remember 3 bromo cyclo 1 hexene. This is the name we can give. And why this product is obtained? Because the free radical, which is present next to the carbon with the double bond, will undergo the hyperconjugation, and that is why this free radical is going to be most stable free radical. Now we'll move to understand the various physical properties, my dear students. Alkyl halides are colorless when pure. Alkyl bromides and alkyl iodide develop color when exposed to air. Melting and boiling points. Methyl chloride, methyl bromide, ethyl chloride, and some other chlorofluorocarbons are gases at room temperature. Remember, my dear students, that when we have only one carbon, we will get the methyl product. So if there is only one carbon bonded with chlorine, one bromine, or two carbon bonded with chlorine and some other chlorofluorocarbon which have single carbon, they are gases at room temperature. But higher members are liquid or solid. So as the number of carbon increases or the number of hydrogen increases, the van der Waals forces are increased, and that is why they are either into the liquid or solid instead. This I am talking about the intermolecular forces, my dear students. Molecules of organic halo compounds are generally polar. They are polar because the polarity of halogen is more than the polarity of carbon. So slightly negative charge is generated on halogen, whereas slightly positive charge is generated on carbon, and that is why they are polar. Molecules of organic halogen compounds are generally polar. Boiling points of chlorides, bromides and iodides are considerably higher than those of the hydrocarbon of comparable molecular masses, because alkyl chlorides, alkyl bromides and alkyl iodides have more polarity. Remember, because alkyl chlorides, alkyl bromides and alkyl iodides have more polarity, uh, more molecular mass compared to the parent hydrocarbon, the intermolecular forces are stronger in the halogen derivatives, and so the boiling point and melting point are higher than comparable molecular mass of hydrocarbon. Sometimes what happens, my dear students, they ask you the question that uh, the boiling point of alkyl halides are comparatively more as compared to the hydrocarbon of a comparable molar mass. So if this kind of question is asked, we can write the answer because we can start it as because alkyl chlorides, alkyl bromides and alkyl iodides have more polarity. This is the first point that we are going to write. Second, more molecular mass. They have more molecular mass even compared to the parent hydrocarbon. The intermolecular forces are stronger in the halogen derivative, and that is why their boiling and their boiling points or melting points are higher for the comparable molecular mass of hydrocarbon. Then we have the next point to study. alkyl fluorides have comparatively lower melting and boiling point. So alkyl fluorides generally show the lower melting and boiling point. Now, as we want to study the physical state, my dear students, let us have a look at this physical states of the various compounds I have given to you, my dear students, so that you can understand it better. Uh, Let us have a look at that if something is there, my dear students. Okay, so you can see that there are various alkyl halides I have written, and I have written their physical state. You can see that CH3Cl is a gas, CH3Br is gas, but CH3I is liquid. CH3CH2Cl2 is gas, but CH3CH2Br is liquid. CH3CH2I is liquid. CH3CH2CH2Cl is liquid. So when the number of carbon become 3, even chlorides have started to become liquid. CH3CH2CH2Br is liquid. CH3CH2CH2I is liquid. So even if there is one iodine is present, the the physical state is liquid. So none of the iodine or none of the iodide compounds are gases. But if you have one bromide and one chloride, if you have one bromide and one chloride with one carbon, they are going to be gases. So this is how, my dear students, we understand the physical state. Even on the basis of the physical state, we can write the order of the boiling point. So the order of the boiling point would be CH3Cl less than CH3Br, CH3Br less than CH3CH2Cl. These three are gases. Then CH3CH2Br, then CH3I, then CH3CH2CH2Cl, then CH3CH2I, then CH3CH2CH2Br, and then CH3CH2CH2I. If I take name, then chloromethane, bromomethane, chloroethane, bromoethane, iodomethane, then chloropropane, iodoethane, bromopropane, and iodopropane has got the highest boiling point we can understand, my dear students. The above order is due to the molecular mass. You can easily understand the order, whatever we have seen is basically because of the increasing the molecular mass. Iodine, the atomic mass is very high, and that is why you can even consider it as an increasing order of molecular mass. More is the molecular mass, more is the boiling point, because as molar mass increases, van der Waals forces are increases. For the same alkyl group, the boiling point of alkyl halides decreases in the order. See, alkyl iodide have the highest boiling point, then alkyl bromide, and then alkyl fluoride, and then alkyl fluoride, my dear students. This order is because in the increase in the mass, the van der Waals forces increases, and thus the boiling point also increases. Iodine has got the highest atomic mass, and that is why we can see this order. Uh, we can even observe that the order of the CH3Cl is less than CH3Br is CH3I, CH3CH2Cl, CH3CH2Br, CH3CH2I. So if we have the same number of carbon, then iodine, alkyl iodide will have the highest melting and boiling point, whereas alkyl fluoride will have the lowest melting and boiling point. The boiling point of isomeric haloalkanes decreases with increasing in branching. Please remember, my dear students, that whenever the branching increases, as branching increases, surface area increases or surface area decreases, sorry, thus the van der Waals forces even decreases. And as the van der Waals forces decreases, thus the increasing branching causes decrease in the boiling point. You can see here that we have the various isomeric with the same 4 number of carbon. So we can have bromobutane, one bromobutane, we can have 2 bromobutane, and we can have 2 methyl 2 bromopropane. These all have 4 carbons, but as the branching increases, you can see the boiling point. Boiling point for the normal or the one bromobutane is 375 Kelvin, but for 2 bromobutane it is 364 Kelvin, but for 2 bromo 2 methyl propane it is 346 Kelvin. So uh, this maximum branching has the lowest uh, boiling point, and no branching has got the highest boiling point. So as the branching increases, my dear students, the surface area decreases, and that is why the boiling melting point even decreases. In dihalobenzene or dihaloarenes, para-isomer has highest melting point. Remember, here I am talking about melting point which is applicable to the solids. So the in dihalobenzenes or dihaloarenes, the para-isomer has the highest melting point as compared to the ortho and meta-isomer, because the para-isomer fix itself into the crystalline form very well. Because in the crystalline form, para-isomer fix in crystal data is better as compared to the ortho and meta-isomer. You can see that I have given you the example of ortho dichlorobenzene, meta dichlorobenzene, and para dichlorobenzene. You can see the boiling point of ortho dichlorobenzene is 453 Kelvin, meta dichlorobenzene is 446 Kelvin, whereas para dichlorobenzene is 448 Kelvin. They are almost similar. There is not much difference, but still we can see that the boiling point of ortho dichlorobenzene is maximum. But when we look at the melting point, which is applicable to the solids, the melting point of orthodichlorobenzene is 256 Kelvin, the meta-dichlorobenzene is 249 Kelvin, but the para-dichlorobenzene is 323 Kelvin, which is very high as compared to these two. And this is what it can be observed, because the para-dichlorobenzene or the para-isomer for the dichloro or dihaloarene fixes well into the crystalline form. Note the boiling point are almost same, still orthoisomer has a higher boiling point than the meta and para. So the para higher melting point, but for ortho higher boiling point we can see. Then we have the next property to study about, which is known as the density. My dear students, we know that density is equal to mass by volume. Bromo, iodo, and polychloro derivatives of hydrocarbon are heavier than water. So if there is a chloro or fluoro, and if chloro and fluoro are single, they are not denser than the water. But bromo or iodo and polychloro means more than one chloro, uh, uh, more than one chlorine atom are bonded to the hydrocarbon. Such hydrocarbons are denser than water or heavier than water. The density increases with the increase in the number of carbon atom or the halogen atom or the atomic mass of halogen atom. Remember, the density increases by increasing three things. Number one, number of carbon atom. Number two, number of halogen atoms, as well as the atomic mass of the halogen. You can see here, I have written the density of the various compounds for normal C3H7Cl. That is normal chloropropane, it is 0.89. Because there is only one single chlorine, the density is less than water or less than 1. But you can see that for normal chloro or normal bromopropane or normal iodopropane, or when we have the chlorine atom more than 1, that is dichloro methane or trichloromethane or tetrachloromethane, you can see that their density is more than 1 and they are heavier than water. Now we should study about the solubility. The haloalkanes are very slightly soluble in water. So this reason may be asked to you in a quite a few times, that why haloalkanes are very slightly soluble in water. So haloalkanes are very slightly soluble in water, my dear student, because for haloalkanes to be soluble in water, hydrogen bonds between the water molecule needs to be broken. These hydrogen bonds between the water molecule are comparatively strong bond and require more energy to be broken. As new bonds or new attraction formed or set up should be stronger than the hydrogen bond among the water molecule and attraction among the alkyl halides. So if you want to check the, or if you want to dissolve the alkyl halide into water, first the newly formed bond should be more stable than the hydrogen bonding, and second, the attraction among the alkyl halide and water should be stronger. So see, whatever the attraction between the alkyl halide is present, the newly formed bond should be stronger than that. But when we dissolve this alkyl halide into water, when attraction are broken between the alkyl halide, energy release is not enough to break this hydrogen bond, and new attraction set up between the water and alkyl halide are not enough or uh, not more strong than the previous kind of attractions, and that is why these alkyl halides are less soluble or slightly soluble in water. Let us understand this with the logic what I have explained. Attractive forces logic. Suppose we have AA, we have BB, and we want to make AB. So the forces between AB should be more than the forces between AA and the forces between AB. Same way, the forces between BB. So the forces between AA should be more than AA. The forces between AB should be more than BB, and then AB is possible. So here, if you take AA as alkyl halide and BB is water, the alkyl halide water interaction is not greater than uh, hydrogen bonding among water, is not even greater than the alkyl halide of attraction, and that is why the interaction or the attraction between the water and alkyl halide is not possible, and that is why the alkyl halides are slightly soluble or insoluble in water. But in case of the organic solvents, now we'll think of the organic solvents, not water, which are non-polar solvents. But in case of the organic solvent, the energy released when alkyl halide intermolecular attraction are broken is enough to overcome the organic solvent force of attraction, and that is why most of the alkyl halides dissolves in organic solvents such as kerosene, petrol, benzene, carbon tetrachloride, etc. So my dear students, instead of BB being water, if we take the kerosene or carbon tetrachloride or benzene or other non-polar solvents, then you can easily understand that AB is more than AA. So the force of attraction between the polar solvent and alkyl halide is more than the alkyl halide attraction. At the same time, the attraction between the alkyl halide and polar solvent is more than